Hello and welcome to the last chapter or the last lecture really that we're going to have about classical uh, physics before going into the last few lectures about modern physics. So we've already had a little bit of modern physics, but with the relativity general and special, but with magnetism, we are very much at the edge of late modern physics, and it relates to what we've been talking about charge, current, everything like that, and as well as a lot of the more simple machines or even more complex machines that control our day-to-day lives. So with that said, I am going to get started with an exploration of bark magnets. So you've what you've probably seen with uh just like magnets that you've been playing with as uh a child or up until today is that magnets are bar magnets, which are what we usually talk about when we talk about magnets, are metal materials that have two poles, a north and a south pole. So if you put the north and south pole of one bar magnet next to the south and north pole of another bar magnet, like you see on the top left corner, then the unlike poles will attract each other while the like poles will repel each other. And then what's interesting about this is we're not going to get into why this happens yet, but what's interesting about this is that if you break a bar magnet up into separate bar magnets, then each one will still have a south and a north pole, which is going to repel or attract the unlike or like, or the like or unlike rather, poles. So this is just a property of them. And then another thing about magnets is that if you have a magnet and you suspend it in the air so that there's no friction, there's nothing keeping it from turning, then it is going to align towards the north magnetic pole of the Earth, which is going to be slightly off from the north geographic pole of the Earth, and is actually the uh, southern pole of the magnet, where the magnetic field of the Earth, because the magnetic field of the Earth is going to be caused by spinning magnetic particles or spinning magnetic metals in the core of the Earth, uh, which is going to be spinning slightly off from the actual geographic pole of the Earth. So the way that you create one of these permanent magnets is you get a material that is susceptible to them, or is susceptible to being magnetized, which is called a ferromagnet. Ferrous meaning iron. So as you see here, we have this Fe bar, this ferromagnetic bar set between a north and a south pole. And if you heat it up, what happens microscopically is that you have a bunch of north and south poles that are in the material from the beginning that are not aligned with each other. So so each of these eventually, or each of these uh, little domains are called, well, they're called domains. But each of the little cut up pieces where the magnetic field is pointing in different directions is called a domain. And as you heat it up and start tapping it, the domains are the little magnets inside of the iron bar are going to align with the magnetic field outside until they become one big magnet, and all of the magnets are pointing from in the same direction. So one of the things that should be really interesting to note is that there is no magnetic monopole, which means that there is no magnetic field that you're going to find, or magnet that you're going to find, that doesn't behave like one of these north-south magnets, that doesn't have a north side and a south side. And that's going to be from subatomic particles, which have an intrinsic magnetic which have an intrinsic magnetic dipole, which is not a monopole. A monopole means one. Mono means one, di means two. So these are all dipoles, and each magnetic field, each magnet that you're going to come across is going to have a dipole, but not a monopole. So each of them is going to act like this north-south in this north-south way that you see compasses act, or the Earth's magnetic field act. It's just that if you have enough domains and they're all pointing in different directions, then you won't notice the magnetic field overall from this earlier section from part A, or number A in the system, or number A in this bottom graphic, which is north and south dipoles pointing in all different directions, so it doesn't align that well. So another thing that you'll see is magnetic field lines, where magnetic field lines are basically are just lines like electric field lines or gravitational field lines like we were talking about, where it's going to inform how forces act on from magnetic bars, or bar magnets, or magnetic dipoles. But the main way that you see it is if you get a bunch of iron filings like you see on the upper left-hand side, and throw them around a magnet, all the iron filings are going to align according to the magnetic field and draw, and they're going to be rotated around until they're aligned with the magnetic field, which is just something that happens because that's the lowest possible energy that they can have. And if you remember all the way back to energy, objects want to be in the lowest possible energy. So one way that we can visualize magnetic fields is by having these iron lines, these iron filing lines. And then another way is just that the magnetic field is going to determine the forces that are acting according to magnetism. So an electromagnet is going to be what all magnetic fields actually are, what all bar magnets, all ferromagnets, all permanent magnets are actually electromagnets, where electromagnet means that you have a current going through some wire or going through some material, and the current is going to cause there to be a magnetic field, which is going to, as you can see, if you point your thumb in the direction of the current, then the magnetic field is going to be in the direction that your fingers curl. So it's going to be all around the current in the direction your fingers curl. So if you get a bunch of a current, you pass a current through a bunch of curls, through a bunch of slink, through like a spring-like shape called a solenoid, then that's going to create a constant magnetic field pointing in straight along the center of the solenoid. So what you see in the right-hand graph is that taking a solenoid will create very similar magnetic field to just a bar magnet. So what a bar magnet actually is one thing, it's based on, for one thing, it is based on the intrinsic magnetic properties of some materials, or some of like neutrons and electrons and protons, each of which has an intrinsic magnetic dipole. So that can be the case. Another way to visualize it kind of is as electromagnetic magnets, where each di each dipole or each electron is just going around in a circle, creating a magnetic field that is eventually going to create a magnetic field like the solenoid that you see in this material, or that you see here. So we say that a solenoid looks like a bar magnet, but really a bar magnet is just kind of a sum of solenoids along caused by the electrons, or caused by the intrinsic properties of the material. So the force is going to be the force that's encountered by a magnetic, or that is caused by a magnetic field, is dependent both on Q, the charge, and the velocity, and the magnetic field, and the angle between them. So force is equal to Q times V times B times sine theta, whereas the force in an electric field was equal to Q times E without the V or any theta dependence. But one thing is that force is perpendicular to both V and B, and it points according to the right-hand rule. So the right-hand rule states that if you have 5 fingers on your right hand, if you point the first 2 fingers towards the velocity, and then the second 2 fingers in the direction of the magnetic field, then the force is going to be coming out the direction that your thumb is. So what this does, what's interesting about this is that the magnetic force can do no work, which means that it can't change the kinetic energy of a system. What instead has to happen is that there has to be some outside force that's causing the magnetic field, or there's some outside material or source of energy causing, which is linked to the magnetic field, which is doing the work when you see, so that when you see a magnet pulling up a car, So if you're in a junkyard and you see one of those giant magnets pulling up a car, what is actually happening isn't that the magnetic field is causing it to move up. What happens is that the battery causes a change in energy, which is ultimately what's going to cause the car to move up. The magnetic field technically does no work. So another thing that's interesting about this is that even though it does no work, it can still have circular motion, because if you'll remember, circular motion is has a force perpendicular to the velocity of the material, or the velocity of the particle or the object or whatever you're looking at. And it also has, which for one thing means that there's no work, because if velocity is perpendicular to the force, as I was saying about magnetic force, then that means that there's no overlap between the direction that the force is going and the way the force points and the way the velocity points. So if this is the case, then velocity uh, is going to remain constant because there's no change in kinetic energy. So we just have a circular motion, a constant velocity through a magnetic field. So if this is true, if we can't do any work with it, why do we care? It's because if there's a current, we can convert this magnetic field, or the energy that's created by that's in the electrical current, can be used using this magnetic field changed into mechanical energy, such as an AC, or yeah, it's just an AC motor. So if you have a magnetic field through a loop of wire, like you see in these two graphs, or in these two graphics, then the magnetic field is going to cause there to be a force perpendicular to the current, as you see there, which is going to it's going to cause there to be a force perpendicular to the current, which you'll see on the first graphic on the upper left-hand side, because magnetic force is equal to QV cross B, which means that it acts on moving electric charges, which means that it acts on current. So it causes there to be a force moving the loop around, which causes a torque, which can then be harvested as mechanical energy rather than electromagnetic energy like it was beforehand. And then I think the last thing that we want to do, there are innumerable values for this. There are just like I said, uncountable uses of magnetic fields and electromagnetism in general. As you can see by the fact that you're watching this on your phone or on a computer. But one of the things that we can do is that there is a quantity, or there's a quality of magnetic fields called induction, where if you have a magnetic field that goes through a coil or goes through a loop or anything like that, and the magnetic field is changing, then that's going to cause there to be a change in it's going to cause there to be a current in the coil or in the loop that's going to cause a change in magnetic field in the opposite direction. So if you have the north side of the magnetic field coming towards there, so that there's a greater magnetic field pointing to the right, as you see in demonstration A, then that's going to cause there to be a current which causes there to be a magnetic field. As the magnetic field pointing to the right increases, so does the magnetic field pointing to the left caused by the current. So basically, what this entails is that if you want to, you can think of the previous electric motors experiment as there being a different amount of magnetic field or magnetic flux pointing through where magnetic flux is the actual thing that matters, not just the magnetic field. It matters the magnetic field times how much that field is pointing through the area of the loop. So as the battery rotates, as the current rotates, or as the loop rotates, then that changes the area that's pointing towards the magnetic field. So this would have a high magnetic flux if you have my finger being the magnetic field and my hand being the direction of, or the face of the loop, or the open face of the loop. As it turns around, the flux gets smaller and smaller until it's completely perpendicular, in which case no magnetic field is going through the loop. So what can happen here is that a current can actually be induced if you have it, if you set it spinning first. It can cause, or I'm not actually sure if you need to set spinning first, but you can, yeah, I think you do. You can cause there to be a current, which is going to cause there to be a magnetic field, which is going to change as the magnetic field or the magnetic flux that you're looking at changes. So what this induction cares about is magnetic flux and the change in magnetic flux. So as long as there's a change in the B field times the area times how much it overlaps, which is going to be cosine of, yeah, it's going to just be how much it overlaps. So it's going to be like work or something like that. But the important part is flux, magnetic flux is given by, sorry, B times A times cosine theta, where theta is the angle between the normal force of the area or of the face and the magnetic field. So flux is B times A times cosine theta. As flux changes, so as you bring a bar magnet closer or farther away, or you change the angle that the flux makes with, or the area makes with respect to the magnetic field, then that causes there to be a reactionary current induced, which causes another B field in the opposite direction of the flux. So this is useful for motors. This is useful for generating AC currents, alternating currents. It's also useful for changing the voltage of a uh, changing the voltage through a step down or step up transformer. So what you have is you have some ferromagnetic material. We're looking at the left-hand diagram right now. You have some ferromagnetic material, and it is looped. It has two loops of wire around it, or two solenoids around the ferromagnetic material. So as current passes through one of them, it creates a magnetic field as seen in the red lines in the ferromagnetic material, which induces a current in the other one, but the current is going to be different, and therefore there's going to be a different voltage across or the current is going the magnetic flux is going to cause current, and that's going to cause a different voltage across the second loops. So what you can do is you can change the voltage from one side of the loop to the other side of the loop, or the one side of the ferromagnetic material to the other side of the ferromagnetic material from loop to loop. And what this allows us to do is we pass, it's called a transformer, and basically when we talk about AC current, we pass massive amounts of AC current over power lines, over the countryside, because we want to not lose that information. We want to keep as high of a power as possible, but we don't want that when it comes to our house. So we have a step down transformer, which changes the magnetic field going through the solenoid, or it causes a magnetic field, which induces a current, which causes a countermagnetic field. But the induced current changes the voltage from the massive voltage that you get outside in power lines that can kill you if you aren't careful, to the 120 volt AC current that goes through, or yeah, 120 volt AC voltage, I should rather say, that goes through your computer. So that is very useful, and I hope that you learned a lot from it. I'll see you next time as we move on to modern physics.